Welcome to the Deep Dive. Today we're tackling a really fascinating challenge right at the forefront of AI image generation. We've all seen these incredible leaps, making images from text. But the real frontier now, it's control. How do we precisely guide these super powerful diffusion models using multiple conditions all at the same time?
Exactly. It's one thing to describe something, but another to say, put this object here looking like this with this kind of structure.
Yeah, think beyond just the text prompt. How do you specify exactly where things should go, maybe using a map or even whose face to use, and actually expect the AI to synthesize all of that information, like consistently?
Right. And the current landscape often has these specialized tools. They're great with maybe one condition, a detailed text prompt, or a specific spatial layout like a canny map. But the real tricky part, combining them. Imagine wanting an image defined by, say, canny edges for the structure, plus the visual style or identity of a specific subject image. Getting those totally different kinds of inputs to, well, play nicely together, that's been a major, major hurdle.
Well, our deep dive today drills right into this exact problem. We're looking at a new framework. It's called UniCombine. And it's designed specifically to be this unified controller for generating images using lots of different conditions. It's not just about, throwing more instructions at the AI. It's more fundamental, rethinking how these different guys can actually work together.
And what's really exciting, I think, from a research angle is its foundation. UniCombine is built on the Diffusion Transformer architecture, DIT.
Right, DIT. Heard a lot about that.
Yeah, and it's a model that's already shown it's remarkably capable for just text-to-image stuff. So using that base allows UniCombine to handle this really impressive range of conditions, not just text, obviously, but spatial maps too, like defining edges or depth, and even reference images, like for specific subjects. Right. It's aiming to be a truly sort of comprehensive approach to multi-conditional control.
Okay, so let's unpack this a bit. What are the core innovations? What makes UniCombine able to actually do this?
Well, there are two key architectural things they've introduced. First, they developed something they call Conditional MMDIT Attention, or CMMDIT Attention for short.
CMMDIT.
Got it. Yeah, it's a pretty clever modification of the standard multimodal diffusion transformer's attention mechanism. It's specifically designed to handle multiple conditions efficiently without the compute cost just ballooning, or critically, without the different control signals interfering with each other.
Interference, right.
Yeah.
That seems like a big problem if you're giving it lots of potentially conflicting signals.
Exactly. And the second big piece is how they integrate a trainable LoRA module. LoRA stands for low rank adaptation.
Okay, LoRA. Seen that used for efficient fine-tuning.
Precisely. And using it here lets the framework have both a training-free mode, which means it can immediately leverage existing models trained for single conditions, and a training-based mode that you can fine-tune for even better performance on really complex multi-condition tasks.
Whoa, hang on. Training-free capability right out of the box. That seems like a huge plus for just, trying out new combinations of conditions quickly.
Absolutely. It really speaks to the elegance of their design, I think, and importantly, to really push the field forward and provide a solid base for other researchers, they also created a whole new data set. It's called Subject Spatial 200K.
Subject Spatial 200K. Okay.
And this data set is specifically designed for training and evaluating models on tasks that mix both subject-driven conditions like use this specific person and spatially aligned conditions like match this depth map or edge structure.
So they didn't just come up with a new method. They actually built the resources, the data, to properly test it and let others build on it. That's always a good sign in research. And the applications they talk about, virtual try-on, putting objects into scenes seamlessly, style transfer, but with precise spatial control, those all sound incredibly useful in the real world.
Oh, absolutely. Imagine the possibilities for, say, e-commerce, content creation, even specialized fields like architecture. Being able to precisely control multiple aspects of an image generation at the same time, it just opens up entirely new creative workflows.
All right, let's dive into the guts of UniCombine then.
Yeah.
How does it actually manage this multi-conditional generation process?
Okay, so at its core, UniCombine builds on recent diffusion model advances, particularly using something called rectified flow training.
Rectified flow, briefly, what's the key idea there?
Think of rectified flow as a more streamlined and efficient way for the model to learn the path from just random noise to a realistic image. And that efficiency becomes even more critical when you're adding the complexity of multiple control signals.
Makes sense. Less wandering around, more direct path.
Kind of, yeah. And as we said, they use the multimodal diffusion transformer architecture, MMDIT, which again has proven really solid for things like text to image.
Right, MMDIT. Remind us, for maybe listeners newer to this, what's the basic structure in this context?
So in a typical MMDIT model for text to image, you usually have two main pathways or branches. There's a text branch and a denoising branch.
Okay.
The text branch takes your prompt, processes it into this rich embedding. Think of it as like a compressed, meaningful code for the text. The denoising branch starts with a noisy image and step by step refines it, using that text embedding as guidance to eventually create the final image.
So two streams of info, text guide, and image refinement working together.
Exactly. Now, UniCombine's big move here is introducing multiple conditional branches. Each one is dedicated to processing a different type of conditional input. So you might have one branch crunching the canny edge map, another handling depth info, maybe another embedding a reference subject image. So instead of just the text guiding the denoising, you've now got this whole set of different conditional embeddings also feeding in.
Right, you're feeding in all these desired characteristics from different angles, but how does it keep them distinct? How does it stop them just sort of interfering with each other during generation?
That's where their idea of a unified embedding sequence comes in. It's pretty neat. They essentially take all these different embeddings, the text one, T, the current state of the image being denoised, which they represent as an embedding X, and all the various conditional embeddings, let's call them C1 through Cn.
Okay.
And they just concatenate them, string them together into one long sequence. So you get X, C1, Cn, Cn. This whole unified sequence then becomes the input for their special attention mechanism.
Okay, so all the info is in one big sequence for the model to look at. Now, tell me about this LoRA switching module you mentioned earlier.
Yeah.
How does that fit into controlling multiple conditions?
Right, the LoRA switching module. It's a really clever way to bring in knowledge learned from single condition models into this new multi-condition setup. Imagine you have a collection of expert modules. These are pre-trained condition LoRA modules. Each one is already really good at understanding and processing one specific type of condition, like edges or depth or the appearance of a subject. These pre-trained LoRAs are then loaded onto the weights of the main denoising branch in UniCombine.
So you're not starting totally from scratch for each condition type. You're bringing in existing specialized expertise.
Exactly. You leverage what's already learned. Now, the switching part is key, because for any given generation task, you might have a mix of conditions, say text, depth, and a subject image. The module needs to activate only the relevant pre-trained LoRA modules for that specific mix.
Right.
It does this using what they call a one-hot gating mechanism. Basically, if a depth map is provided as input, the pre-trained depth LoRA gets switched on. If a subject image is provided, the subject LoRA gets switched on, and so on.
Like flipping the right switches on a control panel for the expertise needed for that specific job.
Exactly that. It lets the framework dynamically adapt its processing based on whatever combination of conditions it receives for a particular image. And it's super efficient because you avoid needing to train completely new, huge models for every single possible combination of conditions.
That's really smart. Flexibility and efficiency.
Okay.
Okay, now let's get into that conditional MMDIT attention, the CMDIT you mentioned. You said it's crucial for handling multiple conditions properly. What's the big idea there?
So the standard MMDIT attention mechanism runs into a couple of main problems when you feed it that long unified sequence with all the conditions packed in.
Okay.
First, computational cost. Attention usually scales quadratically with the sequence length. So if you have lots of conditions, especially high-res ones like spatial maps, that sequence gets really long and the computation can just explode. It becomes impractical.
Right, quadratic scaling is nasty with long inputs.
Yeah. And second, there's that interference problem we touched on. During the attention calculation, where different parts of the sequence attend to each other, the signals from different conditions can inadvertently get mixed up or interfere. This could dilute the effectiveness of those specialized pre-trained LoRA modules you just loaded.
Like trying to listen to too many conversations at once and getting them jumbled.
That's a perfect analogy. So CMMDIT Attention tackles this by using different computational pathways depending on which part of the unified sequence is acting as the query in the attention step. Remember, attention involves queries, keys, and values.
Right, the query is like the seeker. The keys offer potential matches, and the values hold the information to be pulled out based on the match.
Exactly. Now, here's the critical difference in CMMDIT. When the denoising embedding X or the text embedding T are the queries.
Okay, the main drivers.
Right. When they are querying, they attend to the entire unified sequence S. Both keys and values come from the whole sequence. This gives them that global view. They can gather info from all the conditional branches.
Makes sense. They need to see everything to integrate it all for the final image.
And this is the key innovation. When one of the conditional embedding branches, like CI, say the canny map branch, acts as the query.
Yeah.
Its keys and values are restricted. They only come from a smaller subsequence, just the text, T, the denoising state, X, and its own condition, CI. So IIAAX, Crucially, a conditional branch's query does not attend to the keys or values of other conditional branches.
So each condition focuses mainly on its own specific information, plus the overall text and image context, without getting directly distracted or mixed up with the other specific conditions at that attention stage.
Precisely. It prevents that unwanted crosstalk, that entanglement between different control signals when they're initially processing their own relevance.
Okay, that sounds like it would definitely help with the interference.
It does. And this restriction is also what makes CMMDIT attention scale much better, because each conditional query only looks at a small, fixed-size subsequence relative to itself, text, and denoising. The overall computational complexity grows linearly, ON, with a number of conditions n instead of quadratically O and 2.
Yeah.
That's a massive improvement for handling lots of conditions.
That is a huge deal, especially if we want to start piling on more and more types of control. Okay, so that's the architecture. Now, how do they actually use this for training? You mentioned a training-free strategy first.
Yeah, the training-free approach is pretty neat. It works because of how CMMDT attention is designed. Remember, when a conditional embedding CI is the query, its attention computation is restricted to just TXAC.
Right.
Well, that restricted computation is essentially the same attention calculation that a standard single conditional MMDIT model trained only on condition C would perform. The input sequence it sees in that specific calculation is effectively identical.
So the pre-trained conditional LoRA module that you loaded for that branch, it already knows exactly how to process that attention query because it's the same context it was originally trained in.
Exactly. It's like directly reusing that specialized tool for the exact job it was built for within this larger framework. Now, when the denoising X, or text-T embeddings query, they can see and attend to all the individual conditional embeddings separately thanks to their global view.
Okay.
This lets them gather and integrate the information from each condition in a kind of modular way. The authors sort of describe it like a divide and conquer approach. The specialized branches do their thing, and the main branches pull the relevant info together.
So the main integration happens when the denoising and text parts look across all the conditions, pulling info from each specialized branch, which is just doing its pre-trained job.
Wow.
Well, that's a very clever way to combine existing knowledge without needing retraining for every new mix of conditions.
It really is. But the researchers also recognized potential limitation. Just relying on the standard softmax function within the attention mechanism to sort of automatically balance the influence of multiple conditions might not always produce the absolute best fusion of features.
Okay. So the automatic balancing might be good, but maybe not perfect.
Right. Sometimes you might need a more nuanced weighting or combination, and that's where the training-based strategy comes in.
Okay, so what's different when they do train it?
To get that potentially better feature fusion, they introduce another trainable LoRA module, but this one, the denoising LoRA, sits specifically within the denoising branch of UniCombine.
Denoising LoRA. Okay.
Now, here's the crucial part. During training on these multi-conditional datasets, like their Subject Spatial 200K, all those pre-trained condition LoRA modules, the experts for individual conditions are kept frozen. They don't change. Only this new denoising LoRA module is actually trained.
So you keep all the specialized knowledge you started with, but you train this new component specifically to learn how to better combine or orchestrate the outputs from those specialists during the main image refinement phase.
Exactly. The denoising LoRA essentially learns to refine how attention is distributed when the denoising part X queries all the different conditional embeddings, C1, C2, etc. It learns the best way to weigh and integrate them for the specific multi-conditional tasks it's trained on. The paper even shows a figure, I think it's figure 3, where the attention map from the denoising embedding X looking at the subject condition becomes much more focused and precise after training this denoising LoRA.
That makes perfect sense. It learns to pay closer attention to the really important parts of each condition when it's putting the final image together.
Okay, and you mentioned they built that dataset, Subject Spatial 200K. Why did they need to create a whole new dataset? Weren't there existing ones? Well, the main reason was that there really weren't any large public data sets that had good annotations for both subject identity and spatial conditions like depth or edges, altogether for the same images.
Hmm.
Most existing data sets focus on one or the other. You might have data sets with subjects and text, or data sets with spatial maps and text, but not really data sets designed for tasks combining specific subjects with specific spatial layouts. To properly train and, importantly, rigorously evaluate models like UniCombine on these complex multi-conditional tasks, they needed data that had both types of annotation linked together.
So they spotted a gap in the available resources needed for this kind of research and just built it themselves. How did they actually construct it?
They started with an existing data set called Subjects 200K. This one's good because it has lots of diverse subject images with text descriptions.
Okay.
Then they built a pipeline to add the spatial annotations. To get the subject locations, accurate bounding boxes and segmentation masks, they used a pretty advanced object detection model called Mamba YOLO World. It's an open vocabulary model.
Open vocabulary, meaning it can find and identify lots of different objects, even if it wasn't explicitly trained on that specific object category.
Exactly. Very flexible. Then for the spatial maps, they used a model called Depth Anything to estimate depth information for each image, and standard OpenCV library functions to extract canny edge maps, which highlight the main structural outlines.
Gotcha. Depth and edges.
Yeah. So for every image in the original Subjects 200K, they ended up with corresponding subject masks, depth maps, and canny maps, all linked to the original image and text. It creates this really rich, multimodal data set, perfect for this kind of work.
Wow, that sounds like a huge amount of work, but also a really valuable contribution to the community. Okay, so they have the method, they have the data. What about the results? Did UniCombine actually live up to the hype in their experiments?
The results they present are actually quite strong. They tested UniCombine on a range of these multi-conditional tasks, things like multi-spatial generation combining, say, canny and depth control. Also, subject insertion, putting a specific subject realistically into a new background scene. And subject spatial tasks controlling where a specific subject is placed and how it's posed using things like depth or canny maps.
So really covering the combinations they set out to tackle.
Yeah.
How did it compare to other existing methods?
Well, across all these pretty challenging tasks, both versions of UniCombine, the training-free one and the fine-tuned training-based one, consistently came out on top. They achieved state-of-the-art performance compared to a whole roster of existing, often more specialized approaches.
Like what kind of methods did they compare against?
They mentioned benchmarking against UniControl, UniControlNet, Object Stitch, AnyDoor, CRLX, and even combinations people have tried, like using ControlNet together with an IP adapter for subject identity. Many of these were designed for maybe just two conditions or specific types of insertion.
So UniCombine is a single unified framework, outperformed these more specialized tools across a variety of these complex multi-conditional tasks. That's pretty impressive validation.
It really is. The paper has detailed tables, like Table 1, showing quantitative improvements in metrics measuring image quality, how accurately the controls were followed, how consistent the subject identity was kept, and how well it aligned with the text prompt.
Numbers look good. Okay. What about visually? Do the pictures look better?
Yeah, the qualitative comparisons, the actual example images they show in figures like 5 through 8 are quite striking. They visually highlight UniCombine's ability to handle really intricate combinations of controls while keeping the image coherent and accurately reflecting all the inputs. They show examples like combining a specific person's image with an in-painting mask on a background and a text prompt, or precisely controlling the pose and placement of a subject using a depth map while still making sure it matches the text description.
It sounds like it can handle scenarios that were just really difficult, maybe impossible for older models.
Exactly. The authors really emphasize UniCombine's strong semantic comprehension, its ability to understand the relationships between the different conditions. This leads to more accurate placement of objects and better preservation of their visual details. It also showed this really neat ability to adapt or transform subjects plausibly to fit the spatial constraints in the text, rather than just rigidly pasting them in.
And it could still listen to the text prompt, even with all these other spatial and subject controls going on.
Yes, that was another key finding. It demonstrated it could effectively incorporate quite precise textual guidance alongside a whole bunch of other conditional inputs, which isn't always easy.
Okay, and to really nail down why it works so well, They did ablation studies too, right?
Yeah.
Taking parts away to see what breaks.
Yes, exactly. The ablation studies, which they focused mainly on the subject insertion task, gave some great insights. They clearly showed that the CMMDIT attention mechanism really is crucial for getting that top performance. And interestingly, it also helps reduce the overall computational cost by optimizing those attention calculations we talked about.
So better results and more efficient in that respect.
Nice. They also tested where to put that trainable denoising LoRA. They found that applying it specifically to the denoising branch was significantly more effective for bringing together information from multiple conditions compared to, say, applying a similar LoRA to the text branch.
That suggests the denoising stage really is the critical point for merging all these different control signals effectively.
It seems so. And they confirmed that adding this denoising LoRA helped in both types of transformer blocks used in the architecture, the dual stream and single stream MMDIT blocks. Finally, they looked at the overhead.
Right. How much extra compute or memory does it need?
And they showed that UniCombine adds surprisingly little extra GPU memory burden and relatively few parameters compared to some common baselines people use for controllable generation, like FLUX ControlNet or using an IP adapter.
So it's not just more powerful and versatile, it manages to stay pretty efficient resource-wise. That's definitely a win for practical use.
Absolutely. UniCombine really does seem to represent a pretty substantial step forward in making truly flexible, multi-conditional image generation a more practical reality for a lot more applications.
Oh, this is fascinating stuff. Now, let's shift gears slightly for our novel notions segment. This is where we kind of brainstorm a bit, thinking about where research inspired by this paper could go next. Given how capable UniCombine seems to be, what sort of intriguing extensions or totally new research paths could it open up?
Okay, yeah. So UniCombine is great at handling multiple static conditions you provide up front. But what if generation became more interactive, more responsive in real time? This leads to our first novel notion, dynamic condition prioritization.
Ooh, dynamic prioritization. Sounds interesting. Tell me more.
So imagine a designer using a tool based on this. There may be sketching updates, tweaking the text prompt, maybe even just looking longer at certain parts of the generated image, giving implicit feedback. Right now, UniCombine essentially takes the input conditions and runs with them, maybe with a fixed weighting. But what if the framework could learn to dynamically adjust the influence or weight of different conditions on the fly based on these user interactions?
That makes a lot of sense. If the user keeps fiddling with the canny map sketch, maybe the model should start paying more attention to that signal in the next generation attempt.
Exactly. The obvious support is, well, UniCombine already handles multiple conditions. The slightly less obvious path could involve something like reinforcement learning. Could you train an RL agent within the framework to predict the best weights for each condition based on the user's explicit actions like edits, or maybe even implicit cues like dwell time or mouse movements?
Wow.
This agent could potentially learn really complex, subtle relationships between different types of user feedback and the desired balance of conditions, maybe uncovering patterns the user isn't even consciously thinking about.
That's a really cool idea. An AI that learns to interpret user intent, not just from the direct inputs, but from the process of interaction itself. What kind of impact could that have?
I think it could totally revolutionize creative workflows. Imagine architectural design where adjusting structural constraints based on, say, choosing a new material gives you immediate, relevant visual updates that respect both inputs dynamically. Or fashion design, where changing the fit of a virtual garment instantly influences style suggestions based on that change. Even scientific visualizations steering complex simulations by interactively emphasizing different data aspects. It could build on work in interactive ML and maybe RLHF, reinforcement learning from human feedback, but applied specifically to this fine-grained, multi-conditional control problem.
That paints a picture of a much more fluid, genuinely collaborative process between the human creator and the AI tool. Really powerful. Okay, what's your second novel notion sparked by UniCombine?
Okay, my second thought pushes beyond the visual and text modalities UniCombine focuses on now. Think about all the other sensor data becoming available, LiDAR scans, thermal imaging, maybe even detailed audio descriptions of a scene. This leads me to cross-modal conditioning synergy.
Cross-modal synergies. Okay, so broadening the types of conditions even further.
Exactly. UniCombine shows the power of combining different visual conditions with text. Great, but what if we could tap into potential synergies between fundamentally different types of sensory information? The obvious part is, yes, let's add more modalities. The non-obvious part is exploring if there are deeper synergistic relationships to exploit.
Can you give an example? What might that look like in practice?
Okay, imagine this. Could you design a novel attention mechanism, maybe building on CMDIT, that learns to find correlations between, say, a LiDAR point cloud showing the 3D structure of a room and a rich audio description capturing the room's acoustics?
Structure and sound.
Yeah. Could the model learn that certain spatial structures from the LiDAR often correspond to certain acoustic properties in the audio and use that understanding to generate a more realistic image? Maybe inferring material types, like hard surfaces causing echoes described in the audio, or the presence of sound-absorbing objects, even if they weren't explicitly mentioned. This might need, perhaps, modality-specific embedding spaces that then get fused via a smart cross-modal attention layer designed specifically to find these non-trivial links.
That's really fascinating. Using information from one sense, like hearing via the audio description, to actively inform and improve the generation in another sense, vision, in ways that go beyond just listing objects. What could that enable?
Oh, the potential impacts are huge. Think about accessibility generating rich visual scenes from detailed audio descriptions for people with visual impairments. Or robotics improving how robots perceive their environment by letting them fuse visual data with LiDAR or even tactile sensor data for a much more robust understanding. And artistically, it could unlock completely new forms of expression, allowing creators to blend disparate sensory inputs, soundscapes, temperature maps, spatial data to generate entirely novel kinds of art. This would definitely draw on research into multisensory learning and cross-modal representations, pushing how we think about guiding AI generation.
Those are some seriously thought-provoking directions. It's really exciting to see how a solid piece of work like UniCombine can act as a launch pad for these kinds of novel ideas.
Absolutely. UniCombine really does feel like a significant step forward in this whole area of multi-conditional controllable image generation. It offers this unified way to handle lots of different controls and get state-of-the-art results, which is impressive. And that Subject Spatial 200K dataset they built, that's going to be super valuable for the research community moving ahead.
For sure. And as we get surrounded by more and more varied data streams, being able to seamlessly combine and control generative AI across all these different modalities, that's going to be absolutely crucial for unlocking new levels of creativity, understanding, maybe even accessibility. UniCombine feels like a really important milestone on that path. Makes you wonder, what other totally different kinds of signals could we eventually combine to guide AI in creating completely new forms of media or information? Definitely gives you something to chew on.
Indeed. And for listeners who want to really get into the weeds and explore the technical details of UniCombine's architecture, the link to the research paper is right there in the description.
Thanks for joining us for this deep dive. We'll catch you next time.